come to the most important thing about what Turing did. Because Turing, he came up, okay, basically you could say, well, I should tell you this. First came the Turing machine, then came finite state acceptance in the 1950s, right? And Kleene, star operation, and so came after Turing. Turing is the guy who started the revolution. And before that, there was no computers. So I will say more about this when we get to the Turing, universal Turing machine. So, so far, what we did is we said this Turing machine is like a finite state, NFA, finite state acceptor, except that you have to write and erase and whatever. And so then you're thinking, wait, are we a Turing machine? Yes, you're a Turing machine. You're thinking, I don't believe it, right? So artificial intelligence, that trucks can drive on the freeway on their own, and the only trouble is when human beings are there, because if trucks are there, they will drive fast and there will be no problem. But when human beings are there, the truck doesn't know a guy will do a stupid thing. So this is called artificial intelligence, and they have trucks on the road right now that are driving, and they have to cope with crazy human beings who just for no reason suddenly stops and is like, it's like, why the hell you stop? You're in the freeway. Well, I was thinking about my, uh, how I hated mathematics, but don't stop. And this is the problem with human beings. Every one of us are a little bit screwy. Something goes wrong. And so human beings are flawed computers. But at the same time, every once in a while, and you guys are creme de la creme because you're university students and you're doing theory of algorithms and computer science, you are in the top 1% probably, right? Because even if you go to university, you are, in a sort of elite group. But when you're doing computer science, math, or physics, you're in that top 1% of students. And then you're like, oh, okay, thanks. But the point of it is, there are still things about your brain that are screwed. So we said a Turing machine is, you have an infinite tape, which is better than the finite storage your brain has, but your brain has a lot of storage. And we are trying to look to see, man, how come human beings can remember so many things and whatever, right? And this is our problem. We don't understand the brain properly because a computer has more memory. A computer is fantastic in speed, in calculation, but yet, in some respect, a human being is better than a computer. Why? Right? So, again, this is what they are studying in artificial intelligence, etc. So it turns out that a human being has this, this is the price you pay. A human being has this kind of intuitive programming that it guesses and it makes jumps that doesn't seem logical, but because of experience, it factors this in. A computer can learn, yes, but it is a slow learner, and it has to see many examples before it comes up. But a human being, like that, we got a built-in circuit, we can recognize faces. And it took a long time for a computer to recognize faces, and then they have to do a lot of computation. And then the second time, well, either they store it in their memory banks or they saw some important features of the face, and then they realize, oh, this is how human beings do. This guy has a long nose, he has a scar, and he looks a little bit weird. And the human has a way of putting that and storing it in memory. And that's why as soon as you see the weird guy with a little scar, you're like, I know him, Rip Van Winkle or whatever. And you're like, man, you're good. Human beings are good, but they're not perfect. That's the problem. And so we pay a price for these heuristic algorithms. What is the price? We make mistakes. And I am guilty of making mistakes. Every once in a while you'll see I have the wrong symbol, even though I know the correct thing. And so I am just like you guys. No, none of us is perfect. But I keep telling students, don't be perfect, just get 90 or at least 60. And then I am good, right? So if you get 90 or 60, you're good. 90 is A, 60 is C. But I don't want you to get less than 60. And if you get 59, I'll give you the 1%. Okay, so let's look at what it means for a binary relation to be Turing semi-decidable. So we said this the last time, but I'm repeating. Let R be a binary relation and N. We say that R is Turing semi-decidable if we can find a Turing machine such that for the input M, N, M halts in an accepting state if M, N is member of R, and M halts in a non-accepting state or fails to halt if M, N is not member of R. So you're thinking, wait, what is this m comma n? Well, in the Turing machine, you will put your, m here, and then you will put for the comma, you will put a sharp sign, and then you'll put the n here. You're thinking, oh, and then you'll put your head there. So if that's your m comma n. And you're thinking, you mean they will literally have the symbol m? No. So it will be like 3, 4, right? 3, 4 will be like this. That's too long. Hey, what happened to you? Okay, it finally went to 9. 3, 4 will be like this. So this is 3, 4. So that takes the place of the comma, that's the tree, and it's, basic thing. So you're thinking, okay. So when you say m comma n is member of R, we usually say in discrete math MRN. M is related to n. So now we know what it means for it to be semi-decidable. What does it mean to be decidable? And why am I fussing about this? Because this is an important issue. So semi-decidable means you can say yes, and if it's out, you can't really see anything because you could say no, or you might just say, well, go on forever computing, right? And then you're thinking, okay. And then I give you the example the last time of if you have, like, you could ask, does this expansion of pi, does it have 9 nines in a row? Yes, you could look, and if you find it, it has. But if it doesn't have it, you'll never find it, and you will not be able to say, because how can you be sure after 1 billion or 1 trillion digits of pi that 9 nines in a row, it did not occur? You can't say. But if you saw it, you're like, hey, look, I saw it, So you can be sure if you saw it, but if you didn't see it, so that's why it's called semi-decidable. If you didn't see it, you say, well, I was trying a long time and I didn't see it, so I don't know, right? And that's the problem. So if it is there, you will sooner or later get it. It might take a long time, but you will see. So if there is some infinite human being, like some God or whatever, they say God is infinite, he sees into the past and in the future. So God can see an infinite number of things at one time. So God could look at it and say, hey, my friend, there is a sequence of 9 nines in there. In fact, there is a sequence of 12 nines. Seek and ye shall find. Look and you will find it. And then you're thinking, but God, could you tell me where it is? But God is gone by that time. I mean, God doesn't stick around, apparently. So, but at least you heard God said, hey, there's a sequence of 12 nines. So you said, look, I am not interested in 12 nines. I just am interested in 9 nines. Okay, there is a sequence of 9 nines even probably before the sequence of 12 nines. And then you go and you look. But, pobrecito, God didn't tell you how long you have to look, right? And that's the problem with God. He's not showing his face. And that's what makes all the problems happen. Because he could easily come and say, hey guys, look, this is me, I came before and, I and Jesus, that's my son, but he's me. It's confusing, but you don't know. Just look, I'm here. Look, Jesus is there. Jesus, you are Jesus. I am, God the Father. And look, we are one now. See, Jesus disappeared. We joined the one. And that would be good if he did that, but he doesn't want. He wants to keep it a mystery. So nobody knows, and anybody who tells you they knows are lying. So, what does Turing decidable mean? Turing decidable means it's like God showing his face. So we say that R is Turing decidable if we can find a Turing machine such that for this input, M halts in an accepting state if this is so, and then OM halts in a non-accepting state if this is, man, why am I, this is human frailty. If you halt in an accepting state, if this is true, and then I have to put here, this is not true, so I gotta fix that, right? Okay, like I did it here. See, I got it there, but I didn't get it here. I don't know what's the matter with me. So I will clean it up. Clean it up by making this guy a little nice here, and then clean it up by making this guy a little tiny here. Okay, that looks better, but it should be not. You're non-accepting if you're not, but I forgot to put this in. Okay, go back to red. Okay, so now let us show. So you're thinking, you said Turing semi-decidable. So let me clean this up. Turing semi-decidable. Man, I don't like that. I don't know why I can't draw properly. Okay, this is better. So that means if it's semi means you could say yes if it's true. And if it's false, you wouldn't know in a finite amount of time. And decidable means you can decide one way or the other. So I am going to show you that if you give me any two strings, M1s and N1s, I will tell you which one is bigger. So I can say, is 3 bigger than 4? And you're thinking, oh, you have a Turing machine for that. Yes. And so this is the basic idea behind the Turing machine. So I will run on it. I will run the Turing machine on an example to show you what is happening. Forgive me with my nose. And but basically the idea is this. Just like when you were multiplying by 2, you say, hey, you see a 1, put an X, right? And then skip all the other ones until you reach the sharp. So remember, the thing is like, you have 1, 1, right? And then you have a certain number more of ones. And then you have the sharp, right, which is the comma. And then you have 1, 1. And then you have a certain number more of ones. And so you're thinking, okay, skip that and put an X, right? So that's gone, right? And then skip all the other ones and move right until you see that sharp. Once you see the sharp, replace the X by the X, right? And see if you see if any ones, right? So the idea is that, if you see any X, replace the X by the X, and then you move right. So you're not going to see at the beginning, you're not going to see any X because you just left this X, you put that X, you left it, and then you're skipping ones. You're not going to see any X. And if you see a blank, you will say, okay, you have more ones here than here. And you're thinking, okay. That's why you said, if you see a blank early, you go. But if you see a 1, right? So let's say you just have 1, 1. And then you have sharp like this, right? And then you make this into an X. Then you skip all the other ones. So there isn't any one to skip. You right away you go under that. Then you say, okay, skip that, and then look, do you see a 1 or do you see a blank? You say, I saw a 1. So you say, okay, you see that 1, move left and replace that 1 by X, right? And move left. And so you go under that sharp. And then in D, you're like, I am under the sharp. Oh, I can't do nothing. So you stop. And then what does that mean? It means that 1 is not greater than 1. And that's how, I can say if 1 is greater than 2, or I can say it's 2 is greater than 1. So here again in M3 as in M1, we use sharp to separate the input. The Turing machine M3 shows that R is Turing decidable. So Turing decidable means that, you can get the infinite time, yes or no. So let's see how M behaves on 1, 2, when 1, 2 is the input. In monadic notation, this input is 1 sharp 1. So now, I was showing you what happened with the tape here, but that's not the best way. The best way is to do A. So you're in A, and you see a 1, you put the 1 by X, and you move under the sharp, and you go to B, right? B, you don't have a loop there, so that's B, you don't have the loop. So B sees the sharp, and you're like, okay, replace the sharp by the sharp, and go to C, and then the C sees a 1. So the C sees a 1, he says, okay, I have a 1. What do I do? He says, go to D and replace the 1 by the X and move left, right? Because you say, you got an X here, you got an X here. Then when D sees the sharp, D is thinking, okay, go and see if you got more 1s on the left. D sees the sharp, it sees an X. It goes under the X, and that's it goes here to E. So E is now thinking, okay, do I have a 1 or do I have a X? E sees an X and he says, okay, if I see an X, I will go to A, right? And so it goes to A and it moves to the right because X replaces X by A. Then when you're in A and you see a sharp, you're thinking, Senor, what do I do? He's like, You are either looking for a one. If you see a sharp, you hold, so it holds. You're thinking, that means one is not greater than two, right? So you're thinking, okay, I agree. One is not greater than two, and this thing did it correctly. Okay, let us try one more thing. How about two is greater than one? And then I give you homework problem. I give you this, I give you this, all little ones that are short. And this is the hardest, the longest. But let me do two and zero. So you know two and zero is yes. Two is greater than zero. So you're thinking, I will, do this one. And I like to include zero. Why? Because zero is always the troublesome guy, you know? So people don't know how to represent zero. So you're thinking, okay, I am showing you how to represent zero. That's why I give you things like two and one and one and one. This is false, this is true, and this is true, but this has a zero. And then this has a zero, and then this is not zero, but it's long. So you're thinking, okay, I have A, and I want to show the machine. Let me make this a little more smaller because I like to show the machine. So, okay, I can see the machine, and then I can erase you, and I can pull this down a little bit, and I can push this off a little bit there, and I can move this slightly to shoot it up. Okay, good. Okay, so A, you see 1, 1. That's the 2. And then you see 0. So you're thinking, Professor, how did you represent 0 again? This is always a tricky thing. So you're thinking, okay, the sharp is there to tell you what is the second input, and then you don't have any, you have the empty sequence of ones. So because it's all blank after that. So you're saying, oh, that's 0. Yeah, because if I had a 1 here, then it would be 1, right? But I had no ones. So it's like after the sharp, no ones, but before the sharp, 2 ones. So that's the 2. And then the 0 is afterwards. Just like here. I have 1 to the left, that's 1, right? And I have 2 to the right, that's the second input, 2, 1. You're thinking, sorry, 1, 2. 1 is here, that's the 1, and that's the 2. Okay. Now, let's see what happens. A, you see a 1 and you say, I am going to put an X and I'm going to go to B. B, you see another one, you say, hey, skip that one. I will come back to you later. I'm just going to look for to see if the right hand side has any, ones. So B, skip that one. That means it replaces the 1 by the 1 and it stays in B and then it goes under the sharp because it moves one step right. And when B sees the sharp, it's saying, okay, I see sharp, I will replace sharp by the sharp, move right and go for C. So it went to C. C is replace this sharp by the sharp and go to the right. So it's sitting at a blank. And then you're like, hey, it's a blank. So C sees the blank and it's like, what do we do? Blank, replace the blank and move left. So it replaces the blank by the blank and it moves under the sharp sign. That's the musical sharp. Or they call it a pound sign or number sign or whatever. But I call it sharp for music. And then you're like, okay. And then you say, so you went to F and you hold. Yes. And then you are in an accepting state. Therefore, this is true. You're thinking, yes. And the last time we saw 1 was not greater than 2. This time we saw 2 is greater than 0. And then, as I said, these are the problems you do. Now, that is what I wanted to do the last time. I couldn't rush it because I didn't want to kind of, let you miss the point. By the way, since I am eating and drinking or whatever, you may do so also. And in your test and so on, it's okay to eat and drink, right? Not alcohol though. That will make you do bad. So if you're hungry, bring food or whatever. And same thing now, I allow you to eat and so on. Right? But they don't allow you to eat in the classroom at FIT. Okay, so now we are coming to the most important part of this chapter, which is the notion of a universal Turing machine. Then the second thing, the halting problem. And the third thing, the busy beaver function. So you're thinking, usually in question 2, you ask us, what is the halting problem? Write down what is the busy beaver function, and write down what the halting problem says, and then you say some stupid thing about pumping lemma. Yeah, pumping lemma is from the previous chapter. So those are the 3 kinds of questions that can come here, there, and most of the time I do bring that, right? So I am not going to restrict myself, but I'm going to tell you that those are very popular, and why? Because they're important. It says in the syllabus. Sooner or later, you should, well, it didn't say you should ask them in the test. It says you must cover halting problem, you must cover busy beaver function, and you must say what is the pumping lemma. So I did. So what I'm going to do, and then I always try to bring it in an exam. So even though Turing machines are extremely slow and cumbersome, to be truthful to you, it can be shown that for any task for which there is an algorithm, a Turing machine can be constructed to do the same task. And so Turing machine can be constructed to compute all the familiar functions such that, multiplication. I did addition, right? And you're thinking, Professor, I would like to see you do multiplication. Well, I can't because it will take a whole page for a Turing machine. And I used to do it, then the student gave up, and then I stopped. But it has too many states and they don't see what is going on. But the old textbook that we have, Machine Languages by Qualitz and Denning, and that book has the one page of Turing machine for it. So I read this new textbook doesn't have it, and I agree with the new textbook. Why kill students when with complicated things? And then you can do this 2 to the n, and then you can do n factorial. So all of these things I will find different ways of doing this. And then you can find m to the n. This is like 2 to the n, but m to the n, arbitrary. Then you can get wrong the thing. You say, oh, well, this is a complicated function. You take square root of n, like square root of 63 is 7 point something, so it's 7. It's not 8. So you're thinking, okay, you wrong down, okay, that's a function and it produces an integer. And then you can also take the ceiling function. So the ceiling function of square root of 63 is 8. The floor function is 7. You're thinking, okay, so you can do all of this. Now, it doesn't make sense, because why? A Turing machine is a theoretical concept, and it doesn't make sense to do all of these things explicitly because, as I told you, multiplication takes a whole page. This guy here, m to the n will probably take 5 pages. So I don't know, but I have never seen it, but I've seen this. So I'm thinking, why is it that we don't do it? Because one, it doesn't shed great light. You do the simple things, 2n plus 3, 3n plus 2, or 5n or 3n, and you're thinking, okay. And yes, I think you should have seen this, but as I said, there is no time for it because they add in an extra chapter. That's why I also cut it in. So I also would have liked to see something to this, but this is more complicated than that, right? And so whatever the Turing machine is, it's a theoretical concept, and you got to understand that by manipulating the input, you come up with the output, and you're basically giving instructions. Now, this is the greatest thing that has happened to human beings. So, what is the precursor of the Turing machine? Before that, they had built adding machines, and because the people, they had the abacus, and then if you move the thing, you can add with the abacus. But it's not exactly a machine, but they call it a machine. So they said, hey, this thing can help you. You don't have to write and do digit by digit. But the digit by digit, you can make mistake, but that's a fast method. So adding is not a problem. Multiplying, is not a problem. Exponentiation is not a problem. So they actually have Charles Babbage, he and Ada Lovelace, his assistant, and Ada was his programmer, and Charles was, telling her what to do, but basically Ada did all the dirty work, right? And so she should get equal credit. And that's why there's a language called Ada, and there is no language called Babbage. So Charles was lazy. So Charles Babbage, he came up with machines that can do addition and multiplication, that can even solve differential equations. It's more simple. But these are what you call task specific. And the same thing. So for every task, we have a machine that does it. You want a machine for 2 to the n, you call it F2. You want a machine for n factorial, you call it F3. And these two machines have nothing to do with each other. Now, this is where the genius came, of Turing came. Turing says, I will make a machine, M sub u, such that if we are given an arbitrary Turing machine, M, and an arbitrary input omega, we can simulate the action of M and omega. So what Turing did there was basically invent the modern computer. So you're thinking, wait, what do you mean given an arbitrary Turing machine? Well, this is what you do with your modern computer. You want to solve a problem, and the modern computer is like, Turing's ID, and it takes input, right? So you want to know, okay, you want to know the factorize, a 10-digit number. So the guy says, I can factorize a 50-digit number if you want. He said, no, no, please factorize my 10-digit number. So he said, the machine, the Turing, the computer says to you, okay, my friend, okay, you want me to factorize it. Tell me what to do, I'll do it quickly. And then you are saying, what do you mean? You're a computer, do it. No, but the computer doesn't work like that. You have to tell the computer that I want to factorize this 10-digit number, and then tell it how to factorize it. So basically, that's the program. So you have to feed in the program and the input, and this is the brilliance of Turing. It's like, oh, you got to give me the Turing machine, and then you got to give me the input, and then this universal Turing machine will do the job. So a modern computer is like a universal Turing machine. Now, to help you out, these people who manufacture the computers, they don't send it to you blank, because that will be a shame. They send it to you certain built-in functions, and with Word and whatever. And so you're thinking, oh, an operating system, etc. But basically, the Turing machine, the computer should only be an operating system, and then you have to tell it what to do, right? And then give it input. And so that's why you have to put the program. And most of you who are computer science majors have done program. You're thinking, yeah, we have to give the computer our program, and then we put in the input, and then out comes the output. And that's a universal Turing machine. So how does a universal Turing machine work? Well, here's the other part. I would have liked it to show you a universal Turing machine, but it takes 2 pages in the old textbook, and the new textbook doesn't even show. So it's very complicated, and it will take 2 or 3 classes just to explain. So I don't have that kind of time, but I will give you an idea. So the universal Turing machine works like this. Everything has to be done in code. So when you're thinking code, you can think in zeros and ones, but whatever the code is, it could be hexadecimal. That is base 16, right? They love that base 16 or whatever. So it has its code, and it codes everything. It says, hey, you want to, so what you're doing when you're doing programming, you're coding in a higher level language. But if you do, assembly language, everything has to be done from scratch, right? And all of you, I think, did assembly language. So you code everything into the, you code M. So you're thinking, okay, why do you need to code M? Because this universal Turing machine has everything, right, in its alphabet. And you can always come up with Chinese or Japanese or whatever. So they're like, hey, I don't understand your Japanese. Please code it in my language. So you're thinking, okay. So you code your machine in the language of this. Then you code your input in the language of this, because you could give it any crazy input, right? Like, let's say this universal Turing machine works on base 2. And then you want to put things in base 10. You're thinking, look, base 10 is my stuff. The machine says, okay, you code it and give it in as binary. I am not accepting your base 10. Now, the way modern people do it is they already have a built-in thing to go from base 10 to base 10. So they're like, oh, okay. But if you're directly talking to the machine says, yeah, whatever you do, bring it in base 2. That's my thing. Now, not every universal Turing machine works in base 2, but let's pretend ours work in base 2. So it's like, okay, don't go give me your base 10 crap. I want base 2. So you have to give it in base 2 here, base. You have to give this in base 2. And then how does it give you the answer? So it says, you know what? I'm a machine, and I will check your thing. I will check your input. I will check your this. And then it gives you the configuration, just like how I was giving you configuration here. So it codes the configuration too, and it says, okay, this is your input. This is the machine. I will put the initial state of the machine, and I will keep this. I will keep just like here. Say which state, where my head is, and what is on the tape. So it does all of that, and that is called the initial configuration. And it says, okay, now after this, it runs up and down the tape. It runs in here, and it says, okay, I am seeing this. What do I do? And it looks it up in here, right? It doesn't have to deal with this anymore. It already codes that in here, but it has to consult C of M, just like how I look at the machine and I say, hey, if you see an A and you see a 1, you put an X. If you see a sharp, you stop, because A doesn't handle sharp. You're thinking, oh, so if the guy is seeing that same machine, it says, you know, uh, I have my machine in code. I will look it up and see and tell you what to do. And it keeps doing that, right? So it gets the first configuration, which corresponds to whatever I did there to there. Then it does the third one. So each time it gets that. And then finally, it gets the, where is it? It gets the final configuration when it holds. And then, so this Turing machine will know what M will do at each stage. Why? Because it can consult M. It can run into the tape and says, M, when you see this, what do you do? So it is all written there. M tells it. But it is very difficult for it to read because it's all in a line, right? And look at our machine. We read it because it's a diagram. So, but computers can do that. They can, that's why assembly language works and everything. And then you see the Turing machine, M sub U, will know what M will do at each step with the input omega, because it can run back and check in C of M and C of omega, whatever it needs to check, right? And so this brings us a question. It's basically simulating. So at the end, so you're thinking, how does it do what M did? Well, you can see whatever M does, you can, if you want, you can even print out the final configuration. You can print it out like how I did, and I showed you my final configuration here. And I said, hey, I halted, and that's my final configuration. You're thinking, oh, so I was operating like a universal Turing machine. Yes, I was, right? Because I have the machine, I took the input, and I got the output. I took the machine, and I got the input, right? And then I produced the configuration. And you're thinking, oh, but we see with a machine, it can write all of this stuff. It can just produce configuration, but it works inside, and just for the human beings, it makes it look like that. But inside, it's all zeros and ones. And you're thinking, and doesn't it get mad? No, a machine, that's the beautiful thing of a machine. It does not get mad or crazy, but it does break down. That's the problem. So you have to have built-in things to prevent breakdown and say, okay, do you want 3 out of 5 best or 2 out of 3 best, or just 1 in case any so stupid error come and it crashes. So there is built-in safety mechanism for it to not do any stupid thing, just in case lightning strikes or just in case 1 digit goes wrong. It has got built-in protection, and that's called error correcting. And so that's called, which we don't do in this course. So the universal Turing machine does its job, and that's the modern computer. And the only difference between that and the modern computer is this is a theoretical machine, and it has unlimited tape. The modern machine does not have unlimited tape, and it has to cater for stray symbols, etc., or accidental copying wrong or whatever. So it has error correcting codes, so that you really have to get something totally wrong for it to go wrong. But still, computers go wrong. But with all this built-in protection, it goes right most of the time. And so, to be truthful, a computer is an amazing device. When you think of what can go wrong, and you see how many things go right, you're thinking, man, these guys, I don't know, because your generation was born with computers. My generation, when I was in, I think, high school or so, I couldn't afford a calculator because it was very expensive. It was a lot of money. And I said, yeah, okay, calculators exist. Then when I went to university, it was still expensive. But when I got to graduate school in Caltech, then I bought my first calculator, right? But now calculators is a dime a dozen. But the first one was the Texas Instrument. It was like amazing. It's like, oh, you got this little thing and you punch and it works. Wow. Before, what did we use? We used logbooks and we did calculations by hand. So I am a product of that era. And it was not easy, trust me. Now, I want to get to the halting problem, because without that, we are nowhere. So what is the halting problem? The halting problem is basically saying, suppose I give you a Turing machine H. So is there a Turing machine H such that any Turing machine M and any input omega, if we use this as input, H will halt in an accepting state if M halts on omega, and it will halt in a non-accepting state if M doesn't halt on omega. So you basically want to say, look, I'm asking you a basic question. I, I'm going to give you as input, you know, any machine, arbitrary machine, and followed by uh, omega, an input. So I'm giving you a machine, a Turing machine, and I'm giving you input, omega. And then I'm asking you, will this machine halt on that omega? You know, so it's like when you have some people going to the fortune teller, right? And then, you know, you are crazy about somebody, and then, you know, you are asking the fortune teller, you know, some boy or girl is asking, you know, will that person I love, will they marry me or whatever, or will they, you know, be a good husband or a good wife, you know? As a fortune teller, he says, okay, I see your question, and I will tell you, you know, just put some money in my palm. And now they don't ask for silver, they ask for gold. They ask for bitcoins, dollars. You know, give me $50 instead of saying cross my palm with a silver like the gypsy. So it's the same thing here. Now, you're thinking, well, that's easy. All you do is, look, senor, I can find this machine. You know, I can find your fortune teller. You know, all you do is use the universal Turing machine. You put this and you run it. And if the omega holds, you say, hey, look, it holds. And if it doesn't hold, and you're thinking, oh, if omega doesn't hold, then this you can't tell, because what is the problem with the universal Turing machine? It slavishly does whatever M does on omega. So if M doesn't hold, this guy wouldn't hold. You're thinking, oh shucks, that only shows that this guy is semi-decidable. So the halting problem is semi-decidable, but it's not decidable. So you can't do it. And so that's what the halting problem asks. It's basically asking, is this problem that when a Turing machine halts on an arbitrary input, right? Is that problem, right, decidable? And the answer is no, but it is semi-decidable, because if it is true, you can use the universal Turing machine. But if it's false, the universal Turing machine will not halt and you will not know. You're thinking, man, that's a shame. And then he's like, but can't you use, you know, we human beings are brilliant. Can't we use ingenuity? And then they prove, you know, that is impossible. Just like how you prove square root of 2 is not rational, they prove it's impossible. So the answer to the halting problem is no. Even though the proof is important, it is not simply enough to present in this class. So we will refer the thing to the standard textbook. So then I mentioned, one might think, right, that a universal Turing machine M sub u can serve as H, but this is not so. M will halt in an accepting state if M halts on omega, but M sub u will not halt if M doesn't halt on omega. And you want M sub u to halt in a non-accepting state, to say no, but it will not halt. So you don't have a chance. And so the way to look at this is to look at it as a relation. So let us look at this relation, and you can code everything, you know, as zeros and ones, or you can code everything as numbers. So you're thinking, okay, let R be the binary relation of N. So I'm going to code this as numbers. There's something called Gödel code, and Gödel code can code any mathematical expression, including any Turing machine and any input omega, any string. So you're thinking, okay, I believe your Gödel code. I don't need to see it. I believe in coding. You can code anything as natural numbers. And you're thinking, wait, but what do you mean you code? So, for example, suppose I said 36. You're thinking, okay, what does your stupid 36 code? Right? You just give me one number, 36 is 36, what does it code? Well, I say, no, you got to break down the 36. Factorize it, and it will be 2 to the 2 power times 3 to the 2 power. So that codes 2, 2. And you're thinking, oh. And then you say, okay, I want 180. What does that code? And he says, okay, 180 codes, it's 2 to the 2, 3 to the 2, 5 to the 1, it codes 2 to 1. And you're thinking, oh, so the bigger the sequence of things to code, the bigger the number you'll get, because basically you're just factorizing it and you're putting it as the index. Yes. So that's one way to code things. If you want to code a sequence 205, you'll put 2 to the 2, 3 to the 0, 5 to the 5. And that when you're like, oh, that's a number, that codes it. Yes. That's the basic essence of Gödel's coding. But it's a little more complicated because I lie a little bit to keep it simple. So you're thinking, okay, let R be this binary relation on A, which is defined as follows. C code of M as an integer, code of omega as a natural number is true, is member of R if and only if M holds with this as input. And then the essence of the thing is, and it's going to be false, if M does not hold. So that's what the if and only if says, So if it says, if it holds, it's true. If it doesn't hold, it's false. And then you say, then R is not a Turing decidable relation. You're thinking, oh, okay. And so here, these guys are codings of this as positive integers. So the proof of theorem 1 just boiled down to the fact that the answer to the halting problem is no. Indeed, if R was Turing decidable, then we will be able to find a Turing machine with exactly these properties in the halting problem. So people were disappointed, but they said, look, Turing himself was a little bit disappointed, but he said, this is how life is. That's why the world is interesting, right? That you can't do everything you like, right? And so we have found a binary relation which is not Turing decidable. What is the binary relation? The halting problem relation. A universal Turing machine will readily show that R is Turing semi-decidable, but R complement is not even semi-decidable. So you're thinking, wait, what is R complement? So suppose you take the complement of the relation R, right? So you say this thing, you want to know. So you want to know. Tell me. You say, okay, I am not interested in knowing when it holds. I'm interested to know when it doesn't hold, because this is the point when things get interesting. So can you find a machine and forget when it holds? I want to know when it doesn't hold. Can you find a machine that stops exactly in an accepting state when it doesn't hold? And it turns out, no, that is not even semi-decidable. And forget that when it holds, you don't say anything. So you're thinking, man, this stuff is complicated. That, so there is something nice about R, and then there is something ugly about R complement. So you're thinking, oh, this is the guys that R can be half nice, but R complement is not half nice. R complement is like really ugly. And you're thinking, but they're related. But this is the thing. If R is decidable, R complement is decidable. Just like how we were talking about regular languages. If R is regular, our complement is regular. And you're thinking, okay, that's, or L, we were talking about L. So here we are talking about relation. So you're thinking, okay, I agree. That, regular thing. And then we were talking about, non-regular languages. And then we said, okay, non-regular languages, the complement are non-regular also. So if you're bad, your complement is bad. Now, this one is a little different. This thing, the R is half good, but the complement is not even half good. And you're thinking, man, this is not what I signed up for. But whatever it is, that's R. Now, the next follow-up question will come, is like you're thinking, okay, you found a relation that is, not decidable. Okay, I want you to find some function that you can't compute. You're thinking, what are you asking about here? So the things that you can't compute, so I have to, give me, I have to fix this A and D. I don't know why it came like that. Okay, it still looks like and okay, A and D, and there is no little mark there. Thank God for this lousy, but still is good. And that looks like and, I think. This erasing feature of Acrobat Writer. Without that, I'll be dead. So, I am going to ask the question, is there a function that is not Turing computable? So that's why Theorem 2 pops up. And you're thinking, okay, let me see your crazy function that you will come up with. And so what I'm going to do is basically again, and this is Turing's brilliance. It's like, I will find a function that, you don't have a program for. And everything is basically based on this function, right? The halting problem, everything is based on it. And this guy is proved to be not Turing computable because of the halting problem. So Turing came up with this idea and he's like, okay, this is a brilliant idea and I will show you lots of things that are impossible. And so how do you know there is such a function that is not computable. So you're thinking, look, if you can describe the function, I can compute it. Just tell me what it is and I will write a program for it. That's what everybody thinks, right? And I will describe the function for you, but it turns out it's not Turing computable. And you're saying, why? Okay, let's describe it first, right? And of course, I can't give you proofs of these things. They're all going to take 2-3 classes each proof. And we don't have like 10 classes or whatever to prove these things. We just, in 4 classes or 5, we have the second example. Okay, so let T sub n be the set of all Turing machines with n states and input alphabet. This is input alphabet, this. Right? So I want to restrict it because you have n states, that restricts it. And then the number of transitions is restricted because you only have, 1 as the input and blank as the, the tape alphabet. So 1 input you have. You can only put in 1. And you're thinking, okay, that's a reasonable thing. And then since there are only a finite number of transitions between the n states, the number of different Turing machines in T n, and I don't know why the n didn't show up, but this, forgive me, T n will be finite. Okay, and now I'm able to define the function. Let Hn equal to set of all Turing machines with n state and with tape of alphabet this, which halts with the blank tape as input. So Hn is, okay, some of these Turing machines, even though there are a finite number of them, some will not halt because there are Turing machines that says move right, move right, move right, and they never. But we define the busy beaver function, beta maps n onto n, as maximum number of ones a Turing machine in Hn produces when it halts. Now, how do I know it halts? Because I'm picking it, which halts. So let me underline that again. After it started on the blank tape. So you're thinking, oh, why do you call it busy beaver function? Well, a beaver, who does their job. They take logs and they pile them up. So our Turing machine is called busy beaver because it's taking 1 and it's piling it up, right? And it gets a finite number of ones because there's a finite number of machines. And every one that halts will produce a finite number of ones. And then, so this function is not Turing computable. And you're thinking, okay, I don't understand what you mean by it's not Turing computable, right? Well, what does that mean? So let's think about it. Now, it turns out that this function is very, very complicated. And I will go to Wikipedia to show you something, but let me finish this part because I want to show you where you can get extra resources. So the function beta, and they call it beta, it's not Turing computable. Why? Right? Okay, essentially what it does is, in other words, there is no Turing machine B, M sub B, such that, what does it mean to be computable? When you start it at the initial state and you put n, it will produce this. Now, why did I underline the bit of n? Because remember, you have the accepting state, then you have the phi, which is the rough work, then you have the beta of n, which is the string of ones that represent, the number, beta of n, and then you have the underline to say this here is at the beginning of this number. So when I write phi, and then I write C, and then I put my underline there, it says that underline is at the beginning of the string, and then this is to the left. So that's our convention when we're writing things. Now it looks weird, but I don't have any way. Maybe you could put a dot below the beta, but then the dot will think, you're thinking that is beta sub dot or whatever. But then you put the underline and you're thinking, why did you underline it? The underline means, and then you're thinking, how come you didn't put an underline here, right? Well, you're right. I should have put an underline there, right? So let me erase this again. I should have put, there is no underline here on the Q naught, that's a state. But I should have put an underline, like that. I should have put an underline there. Why? Because that the head is at the beginning there, right? And usually I do that. I usually put Q naught omega, and then I put the omega, and so that's your input, and the head is at the beginning of the input, and to the left there is blank, and to right is our blank, and you're like, Okay. We get it. We know what you mean. Okay. Now, I am going to explain in layman terms what is, the reason for this, right? So you're thinking, you can do that? Yes. But the proof is, of course, essentially this idea. So suppose some guy, let's call him Mr. Genius. Mr. Genius maybe he gets some help with his wife because, they say behind every, not a behind, at the side of every great man is an even greater woman. So, like Ada Lovelace, I always like the Ada Lovelace and the Charles, right? And, a good another example, I don't think he's a great man, but, Prince Philip, you have Queen Elizabeth II. And I mean, she's an amazing lady. People don't think so. They think, she's just one crazy old British lady. But no, she was involved in lots of things, that people don't know about. And I mean, whatever she did for the benefit of England. So she is, you cannot underestimate her. You just think, oh, she's a frumpy, old, fat, white lady from England. No, she's brilliant. But, whatever. So let's say this pair, the wonderful young lady and the wonderful young man, Mr. and Mrs. Genius. Let's marry them and so on. And they came up with this Turing machine. And they said, hey, I have a machine that will compute this function. So, and they said, but it's a little complicated. I said, that's okay, come show me your machine. And they said, it has 1 trillion states. I'm thinking, only 1 trillion? And yeah, but 1 trillion is a lot, So it has 1 trillion states and is very complicated, but it does the job. Then I will tell them you're lying. And they will say, why do you say that? I said, okay, you are giving me one machine with 1 trillion states. Do you think that machine could do everything that machines with 1 trillion states can do? That's one machine with 1 trillion states. Can it do everything that a machine with 1 trillion states can do? And not only that, can it do everything that, or see everything that a machine with 2 trillion states or 4 trillion states or 10 trillion states? It can't do all of that because for you to know what is beta of 10 trillion, you have to know how much, wants those machines with 10 trillion. So in one machine, it is not possible to code up what these infinite number of machines will do. And that's the essence of the argument. Because you have to cater that no matter what machine you give me, right? So you have your own fixed machine. It has 1 trillion states. But whatever Turing machine you give me with 100, gazillion, that's not a word, but 100 trillion, say, it has to know what is the maximum number of ones that 100 gazillion state Turing machine can produce. And you're thinking, I don't think that is possible. And then, of course, how do they actually do it? They assume it's possible, and then they do some mumbo jumbo, and they get a contradiction. And it's very complicated. And so if you're curious, you can look into any advanced graduate textbook, but I will tell you, look into the textbook after your exam. Don't get crazy. After you finish the course and you pass, then look. Don't look now. And I tell students that all the time. I said, I don't want you to look at halting problem, just memorize what it says, memorize what is busy beaver function and stop there, right? And don't try to look after you finish the course. Why? Because then that will distract you from the course. Now, this ends chapter 5, right? So I should put it in red. So by the power vested in me, I now hereby pronounce chapter 5 finished. Next time we come back, I get to my favorite subject, which is, recursion theory. And you will see why I like recursion theory, because for, everything we did so far, they were a little crazy, they were not so nice, but I think recursive functions are the nicest. Now, that's my personal preference, but some of you might like grammar, some of you might like regular expression, some of you might like, finite state machine, and those are all simple. And then some of you might hate Turing machines. And to be truthful to you, I hated Turing machines, but I had to do it. I had to do a graduate course for 1 year called Theory of Computation. I did it, and I said, oh, well, okay, it's not that bad. But it was horrible because I didn't like it. But then I started getting to like it. And then why I liked it is because they had the last part of the course was recursion theory. Then I went and did another course on recursion theory. And that's why I like recursion theory so much. So that's the next chapter, chapter 6. And then complexity theory is the last chapter, but you will probably only get just a definition for that. So the last chapter, you will get 2 questions on those, most likely. And so I want to now show you in the last few minutes. So let me save this file. Save. Okay, I want to save that on desktop because whatever I do there, I have to save extre, extra C, and then extra whatever, extra pepper or whatever. No, extra cheese, extra C, extra cheese. Okay, so save. Okay, you are saved. And then I want to go to Wikipedia. Why? I want to type in, and so you can type in too, and you can read. And I'm going to move this away because, Wikipedia. I will type in busy beaver function. Now, this is how you can get things to extend your thing. And you're thinking, okay, where is the busy beaver function? They put this. Okay, I think I want to. Okay, this should be good enough because I wanted to see everything. Now you can see. Okay, so I am not curious. I am going to skip all of that because I have a few minutes left only. And so, okay, they call it sigma instead of beta, but I call it beta because most textbooks call it beta. Even though beta is an uncomputable function, there are some small value of n which is possible to obtain its value and that they are correct. It's not hard to show that sigma 0 is 0. So if you have a Turing machine with no states, it can't compute any one. It does not, it's an empty Turing machine. You're thinking, is there such a thing? Yes, because these mathematicians are crazy, and they call it sigma. And they're like, okay, but can you have one? So if you have one state, you just say, okay, produce a one and then stop. And you're like, that's the best you can do because the moment you try to cycle, you will go into an infinite loop. So the beta of 1 is 1. And you're thinking, okay, beta of 2 is 4. And then they got beta of 3 is 6, beta of 4 is 13, right? And they don't know beta of 5. So if you have, just imagine, you have only 5 states, and they still don't know what is the maximum number of ones it can reproduce by that. And so with 4, they figure out, they show the machine, and so you can, of course, produce an infinite number of ones, but that's not halting. But with 4, they showed you halting, and so you're thinking, it is worth looking into this, of course, after the exams, after you finish the course. Like, how did they get this machine to produce 13 ones from just 4 states? Now, 4 is a lot, 3 is less, and as you notice, 2 is not so good, but, I am surprised it goes 1, 4, 6, 13. I thought it would be 1, 4, 10, 23 or something like that. But 6 is 6. I thought this would be a big number, my hunch. But I can't complain because the people who did it, they checked it carefully. And how did they check it? They check it by hand and they check it with machine. So they use a computer to do the thing and check all possibilities. And then the computer said, okay. Now, my time is up and I wish you guys well. Please do 5 exams. And if you want to know more, there's a whole there's so many things. There's a lot more. I got to put in Miss